Hey guys, welcome back to General Chemistry. Today we're going to talk about Charles' Law. So Charles' Law is our second one in our basic gas law. So remember we're looking at two of the properties of a gas holding two constant. In Charles' Law, we are going to look at the volume and temperature. Okay? So what this chart here tells me on the bottom here, we've got the temperature. So going from left to right, our temperature is increasing. On the left-hand side, we've got volume. So from bottom to top, volume is increasing. And what we see is they're proportional. So as temperature increases, volume increases. Temperature increases, volume increases, so on and so forth. So the relationship between between temperature and volume is the volume of a gas is directly proportional to this temperature in Kelvin. That's going to be important. So again, here's kind of our mathematical symbol of the same statement there. So fishy symbol is proportional to, and we have volume, temperature proportional to one another. All that means is that proportional to means when one goes up, so volume increases, that means temperature is going to increase as well. Or if temperature decreases, that means volume is also going to decrease. So it's just a direct proportionality between those two. And then what do I have highlighted in bright yellow? Yeah, the temperature has to be in Kelvin. So let's think about why this is. What is going on at the at the molecular level? So increasing the temperature will, of course, increase the kinetic energy of those particles. So as we increase the temperature, those particles are going to move faster, right? Now, what are the things that we're holding constant? We're holding the amount of gas constant, and we're holding pressure. So if we increase the temperature and don't change anything else, those particles are going to move faster. They're going to have more collisions with the side of the container. However, we want to hold pressure constant. So as those particles move faster, if we want to maintain the same number of collisions, we're going to have to pull the sides of that container away from those particles. They're moving faster. We've got to give them some more room to work. So that's why as we increase the temperature, the volume has to increase. Conversely, if we decrease the temperature, those particles are going to move slower, and there would be less collisions with the side of the container. So to maintain the same number of collisions, we're going to have to scooch the size of that container closer to those particles in order to maintain the same number of collisions. Okay. So just like the Boyle's law, we're going to have a formula associated with this. Again, I'll spare you the derivation, but because it's a direct proportionality, this formula is going to look different. So the formula is going to look as follows. V1 over T1 is going to equal V2 over T2. So that's going to be our equation, where initial will be on the left-hand side of this equation, final would be on the right-hand side. So let's take a look at an example. Imagine that we have a 2.7 liter solution or gas sample at 354 Kelvin. If we cool the sample to 298 Kelvin, what would the volume be? So for this one, I have highlighted and bolded and put some exclamation points just as a reminder that the temperature has to be in Kelvin. This particular problem gave us the temperature in Kelvin, but if it were to give it to us in Celsius, we would have to convert that. Okay, so let's take a look at this problem. I'm just going to get a little bit of room to work. And the first thing I like to do is I like to take inventory of what I have and be crystal clear on what it is that I'm trying to solve for. So clicking back to our problem, imagine we have 2.37 liters of a gas sample at 254 Kelvin. So that 2.37 is going to be my initial volume, and the 354 Kelvin is going to be my initial temperature. Just make sure I did that right. All right, so if we cool the sample, so this is going to be T2. This is after some time has passed, we cooled it down. We cooled it to 298 Kelvin. And we want to know what's the new volume. All right, now that we have our variables, let's plug them into our equation. So 2.37 divided by 354 Kelvin, that equals V2 times 298 Kelvin. Okay. For these, having those fractions is going to make the math just a little bit more difficult. So I want to show you the way that I solve these. It's not the only way, but it's the best way that I have found. To solve these equations, I'm going to cross multiply in order to get rid of the fractions. So cross multiply is exactly what it sounds like. We're going to multiply on the diagonal. Okay. So I'm going to take 354 Kelvin, and I'm going to multiply that by V2. And then I'm going to set that equal to the other cross multiplication. So this one is the 2.37 liters times the 298 Kelvin. Now we have a formula that doesn't have any fractions. That's much better. And now we can simply divide and solve for V. So those cancel. Whatever I do to the right side, I also have to do to the left side. Kelvin cancels. So the volume of the new volume of our solution, plug this into my calculator. We've got 2.37 times 298 Kelvin divided by 354. So the new volume is 1.99 liters. Again, we can ask ourselves, does this make sense? So our temperature decreased. So with that direct proportionality, we would expect volume to also decrease, and it does. So that's Charles' law. I hope you guys found this helpful.